Welcome to this lesson on TRIZ, the theory of inventive problem solving. TRIZ is a systematic methodology for innovation that was developed by analyzing hundreds of thousands of patents to identify patterns in how inventions solve problems. So what exactly is TRIZ? TRIZ is an acronym from the Russian phrase meaning Theory of Inventive Problem Solving. It was developed by Genrich Altshuller and his colleagues starting in 1946. Altshuller analyzed over 200,000 patents and discovered that most inventions follow predictable patterns. Only about 2% of patents represent truly novel solutions. The core principle of TRIZ is revolutionary. Someone, somewhere, has already solved a problem similar to yours. Your job is to find that solution and adapt it. TRIZ is built on the concept of contradictions. Let me explain what this means. A contradiction occurs when improving one parameter of a system worsens another parameter. For example, making a product stronger often makes it heavier. This is a classic engineering trade-off. You want strength, but you also want lightness. Traditional engineering involves compromise. TRIZ says, eliminate the contradiction entirely. Altshuller discovered that inventors use about 40 fundamental principles to resolve contradictions. Let me show you some of the most powerful ones. Principle 1 is segmentation. Divide an object into independent parts, make it sectional, or increase the degree of fragmentation. Example, a garden hose. A solid hose is difficult to store. By segmenting it into retractable sections, we solve the storage problem without losing functionality. Principle 2 is extraction. Extract the disturbing part or property from an object, or extract only the necessary part. Example, noise-canceling headphones. Instead of blocking all sound mechanically, they extract and cancel only the unwanted noise frequencies using destructive interference. Principle 3 is local quality. Change an object's structure from uniform to non-uniform, or make each part function in conditions most suitable for its operation. Example, tire treads. Modern tires have different tread patterns in different zones. The center optimized for straight-line grip, the sides for cornering, and specific channels for water evacuation. Principle 10 is prior action. Perform required changes in advance, either fully or partially. Prearrange objects so they can come into action immediately. Example, pre-stressed concrete. Regular concrete is strong in compression but weak in tension. By pre-stressing steel cables inside the concrete before it sets, we create internal forces that counteract the tension forces the beam will experience in use. Principle 15 is dynamization. Allow characteristics of an object or environment to change to be optimal at each stage of operation. Divide an object into parts capable of movement relative to each other. Example, adjustable car seats and mirrors. Instead of one fixed position, these components adapt to different drivers and situations. Let me show you how TRIZ applies to real engineering disasters. The Challenger Space Shuttle disaster in 1986 was caused by O-ring failure in cold weather. The O-rings were designed to seal joints in the solid rocket boosters. At temperatures below 11 degrees Celsius, the rubber became too stiff to seal properly. On launch day, it was negative 0.6 degrees Celsius. The contradiction is, we need the O-ring to remain flexible at low temperatures, but rubber naturally becomes stiff when cold. TRIZ Principle 35 is parameter changes. Change the physical state, concentration, density, temperature, or other parameters of the system. Possible solutions. Use shape memory alloys that maintain properties across temperature ranges, or add small heating elements to maintain O-ring temperature above the critical threshold. Or use Principle 1, segmentation. Replace the single large O-ring with multiple smaller rings with overlapping seal zones so if one fails, others maintain the seal. Now let's compare TRIZ to modern approaches like computer simulations, modeling, and artificial intelligence. Is TRIZ still relevant today? Computer simulations and finite element analysis are excellent for optimizing existing designs. They can predict stress, heat flow, and structural behavior with incredible accuracy. However, simulations require you to start with an initial design concept. They answer the question, how well does this design work? They don't easily answer, what design should I create? Think of it this way. Simulations optimize the path you're on. TRIZ helps you find a different path entirely. What about artificial intelligence and machine learning? Can AI replace TRIZ? AI and machine learning are powerful because they learn patterns from data, similar to how TRIZ learned patterns from patents. Modern generative AI can propose novel design variations. However, AI requires massive amounts of training data. For truly novel problems where little data exists, AI struggles. TRIZ works with abstract principles that transfer across domains. Let me give you a quantitative example comparing these approaches. Imagine we need to design a heat exchanger with 30% higher efficiency than current designs. Let's compare approaches. Heat exchanger efficiency equals actual heat transfer divided by maximum possible heat transfer. It depends on heat transfer coefficient H, area A, and the log mean temperature difference. Using simulation, we might vary fin geometry, spacing, and flow patterns. We run finite element analysis on each variation. This could take weeks of computation. If we test 100 design variations, each taking 8 hours to simulate, that's 800 hours of computation time over 33 days of continuous calculation. Using TRIZ, we identified a contradiction. Increasing surface area increases efficiency, but also increases pressure drop and cost. We apply Principle 1, segmentation. Instead of solid fins, use fractal-like branching structures that maximize surface area and minimal volume. We apply Principle 3, local quality. Use different fin geometries in different zones based on local flow conditions and temperature gradients. The TRIZ approach generates a novel concept in hours rather than weeks. Then we use simulation to optimize that specific concept. One of the most powerful TRIZ concepts is the ideal final result, or IFR. The ideal final result is when a system performs its function perfectly while having no cost, no harmful effects, and requiring no resources. You might ask, is the ideal final result even achievable? Usually not completely, but it provides a powerful mental target. Consider music players. We went from phonographs to cassette players to CD players to MP3 players to streaming. Each step moved closer to the IFR, instant access to any music with no physical storage. Each generation reduced physical components, weight, and size while improving functionality. Streaming approaches the IFR. Access any song instantly with essentially zero physical hardware dedicated to storage. Another powerful TRIZ tool is the 9 windows method, also called system operator. The 9 windows tool helps you view any system across 3 dimensions: time, past, present, future, scale, subsystem, system, supersystem. This creates a 3x3 grid. For example, analyzing a car, the supersystem is the transportation network, the system is the car itself, the subsystem is the engine. Then consider each across past, present, and future. By systematically examining all 9 windows, you often discover innovation opportunities that weren't obvious when viewing the system in isolation. Let me show you a famous real-world invention that exemplifies TRIZ thinking, the Fosbury flop in high jumping. Before 1968, high jumpers used techniques like the straddle or scissors jump. They approached the bar and went over face down or sideways. Dick Fosbury did something radical. He jumped backwards, arching his back and going over the bar face up. This looked bizarre but was revolutionary. The physics explanation. By going backwards with an arched back, the center of mass can actually pass under the bar while the body clears it. This is Principle 17 in TRIZ, moving to another dimension. The height cleared equals the height of the center of mass, plus the additional height gained from the arch. By arching backwards, athletes can clear bars higher than their center of mass. The result was dramatic. Within a decade, the world record increased by about 30 centimeters. Today, virtually all elite high jumpers use the Fosbury flop. Let's look at a medical example, the development of angioplasty for treating blocked arteries. The original problem was that blocked coronary arteries required open-heart surgery, which is invasive, expensive, and risky. The traditional solution was bypass surgery. Open the chest, stop the heart, attach blood vessels to route around the blockage. This works but has major complications. The TRIZ contradiction is, we need access to the heart, but we want to minimize invasion and trauma. TRIZ Principle 7 is the nested doll principle. Place one object inside another, or have one object pass through a cavity in another. Solution. Thread a thin catheter with a tiny balloon through the artery from a small incision in the wrist or groin. Navigate it to the blockage, then inflate the balloon to compress the plaque and open the artery. The balloon is inflated to pressures of 10 to 20 atmospheres, about 1 to 2 megapascals. This is enough to compress the plaque against the artery wall. The result is dramatic. Recovery time dropped from 6 weeks for bypass surgery to 2 days for angioplasty. Cost decreased by about 70%. Risk of complications dropped significantly. TRIZ identifies patterns in how technologies evolve over time. These are called the trends of evolution. Trend 1. Systems evolve from macro level to micro level. Mechanical systems become electromagnetic, then electronic, then nanoscale. Example, data storage. We went from punch cards, macro, mechanical, to magnetic tape, to hard drives, to solid state, to molecular storage. Each generation is smaller and denser. Storage density increased from about 10 to the 4 bits per square centimeter in early hard drives to 10 to the 9 in modern solid-state drives, a factor of 100,000. Trend 2. Systems become more dynamic and controllable. Rigid systems become flexible, then adaptive, then self-regulating. Example. Buildings evolved from fixed stone structures to structures with movable parts like windows, then smart buildings with automated climate control, now buildings with adaptive facades that respond to weather. Trend 3. Increasing use of fields. Mechanical interactions are replaced by electromagnetic, thermal, or other field interactions. Example. Cooking evolved from direct flame, thermal contact, to electric heating, resistive heating, to induction cooking, electromagnetic field, to microwave, high-frequency electromagnetic field. An interesting question. Can TRIZ predict future innovations? TRIZ doesn't give you specific predictions like, in 2030 we'll have flying cars. Instead, it shows you the direction technology tends to evolve. For transportation, TRIZ trends suggest evolution toward increased segmentation and modularity, greater use of fields rather than mechanical contact, transition from macro to micro control, increased ideality. This suggests future transportation will be modular, autonomous electric vehicles that communicate via electromagnetic fields, with micro-level control systems approaching the ideal of door-to-door transport with minimal environmental impact. Now let's be honest about the limitations of TRIZ. First, TRIZ requires significant training and experience to use effectively. The 40 principles and contradiction matrix can be overwhelming for beginners. Second, TRIZ is not a substitute for domain expertise. You still need deep knowledge of your field. TRIZ helps you think differently, but you need to understand the physics, chemistry, or biology involved. Third, some problems require entirely new scientific knowledge that doesn't exist yet. TRIZ can't help you solve problems that require undiscovered physics. So what's the ideal approach? Is it TRIZ, or simulation, or AI? The ideal approach uses TRIZ for concept generation and problem framing. TRIZ helps you identify contradictions and generate novel solution concepts. Then use computer simulation for detailed analysis and optimization of those concepts. Simulation tells you which concept works best and how to refine it. Use AI and machine learning for pattern recognition and rapid iteration through design variations. Think of it as a pipeline. TRIZ generates concepts, simulation analyzes and optimizes, AI rapidly iterates variations. Each tool plays to its strengths. Let me share some quantitative data on TRIZ effectiveness from industrial applications. Samsung Electronics adopted TRIZ systematically from 1997 to 2005. They trained over 40,000 engineers in TRIZ methodology. Their patent applications increased from about 5,000 per year in 1997 to 25,000 per year in 2005, a five-fold increase. They reported cost savings of approximately $1.5 billion over 8 years from TRIZ-generated innovations. The average time to solve technical problems decreased from about 3 months using traditional methods to 2 weeks using TRIZ. Let me give you a framework for applying TRIZ to your own problems. Step 1. Clearly define the contradiction. What parameter do you want to improve? What parameter gets worse when you try to improve it? Step 2. Consult the TRIZ contradiction matrix. Find your improving and worsening parameters. The matrix suggests which of the 40 principles to apply. Step 3. Apply the suggested principles creatively. Don't just copy existing solutions. Use the principle as inspiration for your specific context. Step 4. Evaluate your solution against the ideal final result. Does it move closer to the ideal? Can you push it further? Today, there are software tools that implement TRIZ methodology. Tools like Goldfire and TRIZ automate the contradiction analysis and principle suggestion. They also include databases of engineering effects and patents. AI-enhanced TRIZ tools are now emerging that combine traditional TRIZ with machine learning to suggest even more targeted solutions. However, human creativity remains essential. The tools suggest directions, but the innovative thinking must come from you. Let me give you my final assessment comparing TRIZ to modern computational methods. For breakthrough innovations that require conceptual leaps, TRIZ excels. It systematically pushes you out of conventional thinking. For incremental optimization within existing paradigms, simulation and AI excel. They can explore vast parameter spaces efficiently. For complex systems with multiple interacting components, you need all methods. Use TRIZ to identify subsystem innovations, simulation to verify system-level performance, AI to optimize the integration. Think of innovation potential as a function of TRIZ, simulation, AI, and domain expertise. No single method is sufficient. The combination is most powerful. So what's the bottom line? Is TRIZ better than simulation and AI? TRIZ addresses fundamentally different problems than simulation and AI. It's not a matter of better or worse, but of complementary strengths. TRIZ is best for concept generation and paradigm shifts when you need to think outside your current framework. Simulation is best for detailed analysis, validation, and optimization within a chosen design direction. AI is best for pattern recognition, handling massive data, and rapidly exploring design spaces. The most effective innovators master all three approaches and know when to apply each one. Let me summarize the key points about TRIZ. TRIZ is a systematic innovation methodology based on analysis of hundreds of thousands of patents. The core concept is resolving contradictions using 40 inventive principles. TRIZ generates breakthrough concepts, then simulation and AI optimize those concepts. The most powerful approach combines TRIZ for ideation, simulation for analysis, and AI for optimization. TRIZ remains highly relevant in the age of AI because conceptual innovation still requires human insight guided by proven patterns.